Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin and I'll be running through part 1 of problem set 12, Lewis structures. So we've kind of done Lewis structures in the previous problem set. We've kind of gotten a feel for what they look like and how to structure them. But there are a few other concepts that we have to incorporate into Lewis structures that will help us get the most accurate Lewis structure possible. One of those concepts is resonance. Another is delocalization. And the last one that we'll probably cover in most detail today is formal charge. And all of those will have a significant impact on how we represent Lewis structures. So with number 1, explain the concept of resonance. Resonance has to do with the fact that there's no one possible Lewis structure alone. There can be multiple. And so a resonance structure is a way of describing delocalized electrons. We'll talk about that word here in a second, with certain molecules or polyatomic ions where the bonding cannot be expressed by one single Lewis structure. So let's take carbonate. So it's CO3 2 minus. Okay, carbonate looks like this originally, if you do the Lewis structure correctly. Once we get into formal charge, you'll see where these charges come into, but it's going to be a 2 minus. The minuses are both right here and right there. Now, you can kind of see that this double bond could have been on any one of the other oxygens, right? So what we do then is we draw a resonance structure to show that. We say, okay, well, that double bond could have resonated to another spot, okay, where let's say it's over here. And then we have now the negative charge state over here. Okay, so notice how those change. And you could even see another one where we could put the double bond in the last one there. But those are resonance structures. All they're doing is they're showing that the electrons could potentially be bound differently in this ion. Now, it's not going to be the case for all molecules. For a lot of polyatomic ions, it is, because resonance actually influences the stability of an ion. It actually increases the stability of an ion. The reason is because it spreads out that charge. Think of charge, whether it's positive or negative, as kind of like extra weight. If you have weight concentrated on one area, you kind of want to spread it out. Think of it like a high heel, right? If you prefer to be stepped on by a clown shoe than a high heel, because a high heel takes the same amount of pressure. Let's say it's the same person wearing the shoe. It takes the same amount of pressure and puts it in one area, and that kind of hurts, right? And so same with molecules. When they have charges, and those charges are kind of like localized to a particular area, it tries to spread out that charge so it doesn't hurt so much. So that's why resonance increases the stability of a particular molecule, because it spreads out that charge. So what structural features do all resonance forms of a molecule or ion have in common? Well, I've made a list here of things that you can note down. So of similarities between resonance forms of molecules, so resonance structures, the similarities would be the number of electrons, number of atoms, and the way that those are bound. So notice that when I drew this carbonate up here, I didn't change the fact that carbon was the center atom, for example. I didn't put oxygen in the center, right? Everything's still bound the same. All that's changed is the arranging of electrons around it, the distribution of electrons between atoms, okay? So that could change potentially how many lone pairs a particular atom has, or whether there's an extra single or double bond or triple bond, or it could change those numbers for sure. And it could also change the formal charge, right? This oxygen has a formal charge of -1 here and 0 here, okay? So we'll talk more about formal charge here in a second, but those are the kind of main differences between resonance structures. They should always look the same as far as structure goes. They should always be bound the same, but the electron distribution around them will usually change. So let's look at number 4, or letter D here. It says, are the following two skeletal structures resonance forms? Why or why not? Well, notice that it's bound differently, right? We've now changed the way that this is structured. This oxygen was on the outside over here, right? But now we've put it in the middle, and that changes what the molecule is to begin with. And so these are not resonance structures. They're not, because their atoms are not arranged the same way. Sorry, that's horrible handwriting, because not arranged the same way. Okay, so that's kind of how you want to think about Lewis structures, but in particular resonance structures. Resonance structures are simply just a subtype of a Lewis structure. So number 2 says, explain the concept of delocalization. Delocalization means that electrons are not specified. They're not specifically assigned to any one atom or area. In fact, they are spread over an area to increase the stability. It's always to increase stability. And so here we have a resonance structure which doesn't really show delocalization per se. When we get into hybrid resonance structures, you'll see what I mean, where we take all the possible resonance structures together and form them into kind of one hybrid which combines all those principles. That kind of does show us the delocalization, but the principle is that electrons are not specifically bound to this oxygen or this oxygen or this oxygen or even this carbon, okay? So just recognize that delocalization just means not localized. It's not assigned to any one place. So what is the difference between resonance and delocalization? Well, resonance is relatively, I like to say fake, okay? It's relatively fake because no molecule actually ever looks like this. No carbonate ion ever actually looks like that, okay? That's just kind of how we represent it with our human eyes. The way that it's actually in real life, what it looks like is if we were to combine all the resonance structures, let's say I wanted to do the resonance structure for carbonate, I'll show you what this looks like. So the hybrid would say, okay, I know that there are at least 2 negative charges total here, but that the electrons are kind of bouncing around all of these, and so we draw like these dotted lines that looks like this, okay? And what that means, all it's showing is that all that electron density is being spread throughout. And then what the resonance structure does help us do is figure out the bond order, where we say, okay, here's 2 bonds, 3 bonds, 4 bonds. Okay, now 4 bonds, okay, that's all the bonds that you can see, divided by the number of atoms that are being bound to. So this would be 1, 2, and 3. Okay, so divided by 3, this would be a 1.33 bond order. What does that mean? That means it's stronger than a single bond, but weaker than a double bond. A double bond would be a bond order of 2. But because we have this extra electron density and we're spreading it throughout, it's like each bond is slightly stronger because of that extra electron density, okay? So it doesn't actually represent actual characteristics of the molecule. It's just kind of how we use it in our human minds to comprehend this kind of stuff. The combination of all those, like I was saying, into a hybrid resonance structure, like I show here, is kind of the best way to show delocalizations, where electrons are not just contained on this electron or this electron or this electron. And in fact, we actually write lowercase delta negative to show that there are partial negative charges on each of those oxygens, because each of the resonance structures shows one on each of those. So which one more accurately represents reality? Well, delocalization. And delocalization, because it shows that it's able to, remember that delocalization decreases the instability or increases the stability of those ions, because, and this is actually what the real structure of those ions will look like, okay? So delocalization is more accurate of reality. Resonance kind of helps us keep track of electrons and where the negative charges are, or the formal charges, I should say. But other than that, for the most part, delocalization is going to be our reality, or the hybrid, I'd say a hybrid resonance. Okay. All right, so number 3, draw another valid resonance structure for each of the ions given below. Use a correct resonance arrow between the resonance ions. Okay, so here I've got a molecule, and I'm going to write the double-headed arrow. So that's what we do for resonance structures. And then the key is writing everything the same. So here I've got hydrogen, or the bonds the same. Okay, so then I'm going to put oxygen up here, and then oxygen down here. Now you'll notice I put a single bond here and a single bond here. That's because what I'm doing now is I'm recognizing, okay, now I have a double bond here. It could have been over here though. So I'm going to say, okay, what if this was double bound and then this had the extra lone pair, and that would be a negative charge. So these right here would be resonance structures of each other, okay? Because technically this negative charge could be there, or this double bond could be there as well, right? So that's a possible resonance structure. All right, for part B, we've got oxygen. We've got this structure here. I'm going to write my double-headed arrow, and then I'm going to structure everything the same. Okay, everything is bound the same. Okay, and then I'm going to put the 2 electrons here. Now, I do have a positive charge here, but what we can do is whenever you have a lone pair, if there's an area to make a bond, if carbon isn't saturated with all its 4 bonds, you can actually make another bond with it. So I'm going to pull these down and make them into a double bond here. So if I do that, it looks like this, okay, which leaves just the 2 electrons on the oxygen. And if we were to do the formal charge on carbon, now it would be 0, but we have to conserve charge, right? That positive doesn't just go away. We actually now becomes part of the oxygen, which we'll get to here once we do formal charges. In this problem set, actually, is when we start to do those. Okay, so this would be the next resonance structure for this molecule, all right? Now, number 4, nitrogen-fixing bacteria convert urea into nitrite ions. Okay, draw the Lewis structures for the 2 species. So now, I want you to draw this and then draw the nitrite ions. So let's start with what would be the center atom here, right? Remember, when we're drawing Lewis structures, we want to figure out what the center atom is. And without expanding the octet, carbon is going to be our center atom, okay? Most of the time. I'd say 99.99% of the time, carbon will be a center atom, okay? When we have an oxygen in parentheses like this, what that means is that it's trying to designate that oxygen is explicitly and only bound to the carbon, which in that case would have to be usually a double bond. Unless there was a negative charge on this thing, you may assume that it's a single bond, because that would give it a negative formal charge. But for this case, let's try a double bond and see if it works out. So now I've got these two nitrogens on each side of this carbon. So I'm going to say nitrogen here and nitrogen here, and each of those hydrogens are bound to that nitrogen there. And then I'm going to give everybody an octet. So thus far, all I needed to do was put these lone pairs on these nitrogens. And you'll actually find out, I'm not going to go through the whole numbers and counting, but you'll find out that this is actually what the Lewis structure looks like, okay? So that's what you would draw for the urea. And then nitrite, remember nitrite ion is that, NO2 minus. That's just one of those polyatomic ions you just have to have memorized. So here I'm going to assume that nitrogen is the center atom because it can make the most bonds without expanding its octet. So I'm going to put nitrogen here, 2 oxygens, and then give everybody an octet. And then count to see if I've met it. So I've got 5 here, 2 times 6 plus 1. So that's going to be 18 valence electrons. And I've got 18, and then 20. So I've got 2 extra. So remember, when we do that, we're going to cancel out 2 lone pairs. So let's cancel out this one, and then make a bond where those would have been, to then have a net loss of 2 electrons so that we can get to where we need it to. So now I've got 8 here, and now 18 here. So now we're good. And this is an ion, and the negative formal charge is right there, so you can write that. Now they've asked us to include all resonance forms. This does not have a resonance form that you need to worry about. Technically, what we could do is make this lone pair a double bond, but then that would kick this double bond up into a lone pair on the oxygen. That's it. It won't do that, and we're not going to draw that because it's actually unstable for it to do that. Because if we did that, we'd actually create charges. We'd get a formal charge here and a formal charge there, and having charges is much less stable than having neutral. So you actually won't write a Lewis structure for the first one, but you can kind of see that in this one, this double bond could have easily been on that oxygen there. So I'm going to write oxygen over here, double bound, nitrogen, lone pair, and then that oxygen right there. Okay. All right, so that would be your Lewis structures for nitrite. And then part B says, draw a Lewis structure for the bicarbonate ion. Show all resonance forms and non-zero formal charges. What is the bond order of each carbon to oxygen bond? Okay, so now in part 2, I'm going to be covering 5 through 7, and we'll be talking way more in depth about formal charges. But there's something, but in this problem, this is where I'm going to introduce how to do this, and it's actually a lot easier than you may think. Okay, so to draw bicarbonate, you have to first know what carbonate looked like. Okay, carbonate, remember, is CO3 2 minus, and then we're trying to ultimately draw HCO3 minus. Okay, all this did was add an H plus. Okay, H plus. So when I draw this, I got to have carbon in the middle, and then I'm going to draw my 3 oxygens that are bound to it and give everybody an octet. And then you'll notice that later we would have had to draw a double bond somewhere. So I'm going to draw that there. Now, here's the key to formal charge. Okay. What you do is you look at each individual atom and figure out, based on where they are on the periodic table, how many valence electrons are in their shell, and based off that, how many valence electrons are actually assigned to them in the Lewis structure, and take the difference between the two. Let me show you what I mean. Okay, what I do is I say it's want minus have. Okay, what they want, minus what they have. So for oxygen, for example, because it's in the 6th group on the periodic table, it's got 6 valence electrons. So it technically wants only 6 electrons assigned to it. Yes, it has its octet, but formal charge is not talking about whether it has an octet or not. It's talking about which electrons in the octet are actually assigned to that atom. Okay, and so in oxygen wants 6 around it. Okay, that's going to be consistent throughout. Anytime you do it with oxygen, it's always going to be 6. Now, have will always depend on the Lewis structure. So let me put PT up here for periodic table, because that's where you're going to get this. And then for have, where you're going to get this is the Lewis structure. So I'm going to put LS, okay? So what they want comes from the periodic table. What they have comes from the Lewis structure. And this is how we count these in the Lewis structure. So looking at this oxygen right there, you always count both electrons from a lone pair. So So remember, each line here is 2 electrons, so I'm going to count 2, 4, 6. Okay, those are all the lone pairs that are on oxygen, and all six of those electrons belong to oxygen. And then when we're looking at bonds, we only count half a bond. So 1 electron is assigned to this one, and 1 electron is assigned to oxygen. Okay, so that means it has 7 here. Okay, assigned to it, right, according to formal charge rules. So 6 minus 7 is equal to -1, which is where we get that negative charge from. Okay, so when you saw when I was drawing that earlier, the carbonate ion, that's where we're getting that. Okay, that's where this minus charge comes from, is where we're doing this. So I'm going to put the minus charge on the other one because it's the same. But let's do this one really quick. Okay, so I know that it wants 6 because it's in the 6th group on the periodic table, but it's got 2 lone pairs. Okay, so that's 2, 4 electrons that are assigned to it, and then we can count half of each of these bonds. So 1, 2. Okay, so that's a total of 6. Okay, so that has a 0 formal charge because it has 6 and wants 6. So this is actually incredibly stable. When we have a 0 formal charge, that's a good thing. We like having 0 formal charges. In fact, most of the time when we're drawing Lewis structures, when it's a 0 formal charge, we don't even put the 0 in there. We just kind of leave it out because we just assume that if it's not listed, that it's just going to be 0. Okay. Now, really quick, let's look at carbon. Carbon, where is it on the periodic table? What does it want? Carbon, I'm going to put, let's say carbon. Carbon wants 4. Okay, it wants 4 because it's in the 4th group on the periodic table. Now, what does it have? It's got 1, 2, 3, 4, half of each of those bonds. So I'm going to say has 4. Okay, which means it has a 0 formal charge. Okay, so I'm not even going to list it there because they only want us to list non-zero formal charges. Okay, now we kind of touched on this earlier. What is the bond order? Now the bond order would be, let's say I took just like, let's say it's carbon triple bound to oxygen. Okay, this would be a bond order of 3, right? That's a triple bond. Or carbon and carbon dioxide. These are each double bonds, which is a bond order of 2. The reason that it works out this way, let me show you why. Because we take the number of bonds, so 2, 4, 6, 1, 2, 3, 4, and divide it by the number of atoms that carbon is bound to, so 1, 2. So divided by 2, that's going to be a bond order of 2 for each of those bonds. Where here, let's say I've got 3 or 6 there, 6 divided by how many atoms, it's bound between that and something else, so it's divided by 2 because it's between 2 atoms. In this case, we'd actually count both the carbon and the oxygen, but when we're talking about the other structures, we're only going to count the oxygens. Okay, so this would be a bond order of 3. So now if we're looking at this, it's important to recognize that you can have a non-whole number integer for bond orders. Okay, you can have something like 1.5 or 2.5 or 3.33, or not 3.33, but 2.33 or something like that. Okay, and so what you do if for bond order, okay, I'm just going to say number of bonds, okay, divided by number of atoms. Atoms bound to center atom. Okay, so number of bonds, in this case, the number of bonds is 1, 2, 3, 4. Okay, so we got 4. And there are how many atoms bound to the center atom? We got 1, 2, 3. We've got 3. Okay, so that's going to be a 1.333 bond order. Okay, that's a 1 1/3 bond order, which means that each of these electrons, there's no actual double bond in here, right? We've drawn one here in the Lewis structure, but remember, that's not actually how this looks. This is a resonance structure. This is not a delocalized hybrid resonance structure, okay? The hybrid resonance structure is what I drew earlier, where we'd say, okay, based on all the Lewis structures, we'll combine them to make them look like they are delocalized. They're not actually bound to one area. So what you do is you draw a single bond to each of the oxygens. You leave each of them has 2 lone pairs because in each of the resonance structures, they always have 2 lone pairs. And then draw a bracket and then draw these like dashed lines between where the electrons would be moving. Okay, and it's like a cloud, okay? It's a cloud of space where all these electrons are doing. Now, you'd put like a partial negative, and a partial negative because at some point in each of the resonance structures, each of them has a -1 charge. And so this is what this would ultimately look like. I know they didn't ask for that, but that's the biggest difference. And that's kind of how you'll kind of understand the bond order, because now you can see, oh, hey, here's a single bond on each of these, and each of them must have within this range here, these delocalized electrons, an extra strength of 1/3 of a bond. Okay, something like that. All right, I hope that was helpful. I'm going to move on to problems 5 through 7 in the next video.